So please write down your thoughts on the sheet of paper here. Grab one, pass it back. Put your name on it. Give me a second. Put your name and last name. Put today's date. All right. Need some more? Okay. All right, so what relationships can you remember between degrees and radians? What was that stuff? How did they play together? And write it down, yeah. If you don't remember, it's okay, yeah. That's, we're gonna start with that, so don't worry. Okay? Anything that comes to your head, if your thing that comes to your head is, I have no idea what a radian is. Start thinking of those words and maybe anything that pops into your brain. And if nothing pops into your brain, that's okay.
It's like something I'll remember as soon as you start describing it.
That's probably, yeah, probably. You could draw shapes, you don't have to write words. Just anything that is your brain.
It's like radius, like a circle thing.
Yeah. A good one. We will most likely use up the entire class time today, okay? Just give me the heads up.
The next class.
The next test would be, I think 3 or 4 weeks.
It's like 2 weeks around after break.
I think so, yeah.
So that means it's gonna be like 4 or 5 weeks until the final.
I think so, for like maybe 3 weeks. Yeah, it'll be only on Trig next time. Yeah. All right, guys. So whatever you have, just check in with your classmates. Maybe they remember something a little different from you. Same usual groups. Check in with your classmates.
Or apply everything in Radians.
Bring it back, bring it back. Walking around, I saw some things. Let's see, just kind of share out. I'm gonna pick randomly here. Someone wrote for their name, LAAF.
Oh, did you collect these already?
Oh, no, oh, Logan, he's not here. Luna. What, just share whatever your group, some things that your group put down on their thoughts, anything. I saw a shape, I see a shape on your thing.
I draw, like, shape, big,
Circle,
unit circle.
unit circle,
The unit circle.
okay. So let's see, so I see something like that, and then I see you kind of divided it like this, looks like a little pizza. Okay, and then you guys are calling this a unit circle. Okay, so we're definitely gonna mention that. Thank you. Aleka's not here. Shirley. Oh, were you in the same group?
Yeah.
Okay, let me have someone else. Hold on. Rohan.
Yeah. Any degree ending with the number 5 correlates to the radian x pi over 4.
So any degree ending with what?
Ending with 5.
With 5 correlates. What did you say?
To the radian x pi over 4.
Radian x pi over 4. Cool. Okay. Thank you.
Yeah.
Let's see, and Rebecca. Rebecca's here. Yeah, Rebecca's not here. Go with the next one. Aldo. Anything that you guys wrote down?
Just, it goes in order from like 30, 45, 60,
60,
90 to 360.
all the way around, okay? I'm not gonna write all that, but yes. Yeah, so you do kind of start with 30, there's a 45, 60, 90, and so on, right? All right, cool. So there's circular shapes, yeah.
Oh,
Want to add a little bit?
pi over 2 is 90 degrees.
90 degrees,
Pi is 180.
pi is 180,
Pi over 6 is 30 degrees.
pi over 6 is 30 degrees,
Pi over 4 is 45.
and then I'll stop with that. Pi over 4 is 45 degrees, right?
Yeah, I can tell you pi over 3 if you want.
Go for it,
60 degrees.
60 degrees, okay. Question, yeah.
Does pi r squared have anything to do with this?
It could, yeah, it has, that's usually pi r squared, the area of the circle. Okay, I'm not gonna focus on the areas of the circle. The textbook on this section does, but like I said, I'm gonna focus only on like the main parts of it. Okay, guys, perfect. So turn in your warm-ups. All of this will definitely be used today. You're gonna see all of it. Okay, but we gotta remember how it speaks to itself and what's the story behind it. Especially the spy business here, that students just start like, what the hell is that? I know I know how I'm using it, I don't know what it is. So we gotta make sure we know what that is. Okay?
I think the weather is mostly in the word.
Okay, guys, so do this. All right, so we're gonna start with section 7.1, and first we're gonna start with what a radian angle is going to be. Okay. Okay, guys, so growing up, you guys learned that you have to measure things, and the first thing you probably learned to measure is how far did something travel. If I'm here and I went this far, I want to figure out how long that is. Okay. So you first learned how to measure distance. And by measuring distance, we also learned to do it with a whole bunch of different units as you went throughout your life, right? So if there's an object that's here, and then it moves this far in this direction, you learned about measuring that with different units. So like, let's say that this is from here to here. Let's say this is 3 feet. That's one way of measuring that distance. But then you also learned about inches. And you learned about equivalent units measuring the same distance. So if something moved 3 feet, how many feet or how many inches did it move?
36.
It moved 36 inches. How many yards did it move? How many feet are in a yard? 3 feet. So 3 feet is also equal to 1 yard. And then you guys learn Halley units, miles, and all these other things, right? Centimeters and all that. So distance has a whole bunch of different units of measurement. Okay. And you also learned that there are some equivalences between these different units. Okay. So then this is measuring how distance moves. And then we have the measure of angles, which is also how much something is rotating. So measures of angles of rotation. So here I'm actually going to write this whole thing out. So to measure how much something rotates from one point to another, you learned the measure of an angle. What's the first type of measure of an angle that you learned? When you were in geometry, what were the, see how here, here, actually, let me write some stuff down. So let's say we're going to draw an angle. There's a starting side. The textbook calls this the initial side. Okay. Let's say there's this point, and then I'm going to rotate it. I'm going to rotate this initial side. Let's say up to here. The side where you ended the rotation, this is called, the textbook calls it the terminal side. And the measure of the angle is how much rotation happened to go from this initial side to this terminal side. Okay. And then in geometry, you learn some notation that sometimes is used in, it might be used in this class. You said, okay, let's say this is the line, a segment connecting the points A and B. And this is a line segment connecting the points B and C. Okay. Theta is one of the Greek letters here, is a common letter used to represent angle. Okay. And so here I can write this angle in different ways. I can say it's the angle theta. And then in geometry, you learn this like little angle notation. I can say it's the angle B. Or I could also say it's the angle ABC, where it's understood that whatever is in the middle is that angle, is where the angle, where the two sides connect.
Does it matter if you do CBA?
If you do CBA, you can also write angle CBA, as long as it's in the middle. The B is in the middle. So there's all kinds of notation that you learned to kind of talk about the same angle. Okay. So when you guys did distance, though, you used units to measure that distance. Now to measure angles, what's the first unit that you learned in your geometry class? You learned degrees, right? You learned about degrees. Okay. And so then the units that you used were degrees, and then you took a trig class, and then what was another unit that you learned? Radians. Okay. And radians. So just the way you learn different units to measure distance, And you also learned that some units have a equivalence relationship to a different unit. That's where we're gonna start today, is there's a relationship between the units of radians and degrees, and we're gonna find that relationship that they have with one another, okay? All right, so let's do some angle remarks and definitions. Revisit some of these things. So let's start with describing the direction in which you rotate something and measure it with an angle. So we're going to say positive angles correspond to, you guys remember, counterclockwise. So clockwise is the way, oh damn it, there's no analog clock here. Clockwise is the way an analog clock rotates. Counterclockwise is the opposite direction. So counterclockwise direction, or sorry, rotation. So that would be something like this. Sorry for the squeakiness. So in math, when something rotates counterclockwise, we're gonna either call it that rotation in degrees or radians, but it'll be positive. Okay. Negative rotation. Sorry, negative angles correspond to clockwise rotation. So they rotate in the direction of a clock, and clock like that. And so let's do some examples so you guys can see. Let's look at positive. So let's say you have a terminal side here, sorry, your initial side's here, and then it rotates up to here. What kind of angle is that? Oh, sorry. Let me actually put the degrees. Yeah, let's say this is 90 degrees. That's called a what? A right angle, right? And sometimes they just write a little square to represent that. So that's where you have your initial side here, start in this direction, and then you rotate it up 90 degrees. But I can also rotate my initial side. Keep going, keep going. I could do one full rotation and then keep going. Okay. So in that case, oh God, I hope this color works. Let me see. And in this case, let's say I go like this. I do one full rotation and then I go back and I end up here. So one full rotation is 360, but then I rotated another 90 degrees. So that would be 360 plus 90, 450 degrees. So this is 450 degrees. Can you guys see that in the back? Yeah. Okay, yeah, you can see that recording too.
Wait. Sorry, I don't like this question seems.
No?
So like, if you're rotating, let's say you're given a degree and then you rotate one,
Mhm.
and then if you're adding, basically that's the positive, it will be positive. And then if you're going the other way, it would, you'd be decreasing, so like you'd be subtracting.
Correct.
Okay.
Correct. So in this example here, if I rotate 90 degrees, the initial side, sorry, if I rotate 90 degrees, or if I rotate positive 450 degrees, the terminal side ends up exactly as the same as a 90 degrees. Okay. Anybody remember what happened, what these angles are called when that happens? Coterminal. Correct. So this is here, 90 degrees and 450 are coterminal angles. And that's when two angles that have the same terminal the same initial and terminal sides. So you would say they're coterminal. Let's do one where here's 90 degrees again. Here's 90 degrees, positive 90 degrees. But now let's say I rotate clockwise and I go like this. So now I'm going the opposite direction. So that's going to be a negative angle. Okay, let's see. So negative 90,
Subtract 90.
another negative 90, and another negative 90 is negative 270 degrees. Okay,
So can we think of it as like subtracting 90 from 360? Or no? So it's over 360. So like because
you can think of it as negative 360 plus 90,
oh, okay,
like that.
okay.
Yeah, that would give you the same result.
Okay.
And let me change my notes. I put negative 370, and that's wrong. Okay. So in this case, negative 270 and positive 90 are again coterminal angles because the initial side and the terminal sides are the same. Okay. Let me do another one. Let's say it's like this, like that. Where's mine? Let's say this is 135 degrees. So with your classmate next to you, figure out what the negatives are. What's that negative degree there? Don't shout it out. Let me have you guys think about it with your classmate. What's the degree here?
Professor, are we going to be working with degrees in seconds?
Degrees in
Minutes, seconds?
no.
That was so stupid. Like, why did we do it?
You learn it when you're doing more like I guess like in the science of astronomy, because you need like tiny little angles.
They wanted you to do an extra step.
Actually, you guys are totally right. There's degrees. There's more, right? Minutes, yeah, arc minutes and arc seconds. You guys are totally right.
Does that come up?
We're not gonna do these though. Yeah, those are in astronomy, when you need something smaller than a degree.
Does that happen in like upper calculus?
No,
You kind of just stick with your brain.
it could happen if your degree is like 0.005 or something, and you want to express it in a different way. It'd be kind of like if something's smaller than a foot, then you probably want to go to inches. It's kind of like that. All right, guys, what'd you get? Negative 225, right? So one full rotation would be negative 360. And then if you add positive 135, you get negative 225 degrees. So this should be negative 225 degrees. Okay. All right, good. Keep going. Got some residual angles, some vocabulary to remind you what things are. All right. So let's focus on these two units now, degrees and radians. So degrees, again, we're still like doing remarks here. So degrees are primarily used when working with angles and geometric shapes. It makes the math a little easier when you're dealing with geometric shapes. Or at least that's how you first started, right, in geometry. And radians, which we're gonna define in a little bit, are primarily used when working with trig functions and calculus concepts. Makes the math a little easier.
Geometric shapes kind of phase into calculus concept a little bit there.
They do, and so that's why sometimes you go from radians to degrees, degrees to radians.
Okay.
Yeah. Mhm.
Is that like when you like trying to like do like the integral of like a shape of like a I don't know how to describe it.
I think it's more when you're like what the stuff you did in geometry, like the sum of angles and checking that geometric shapes, like given a polygon of, let's say there's like a regular polygon with n sides. What are the degrees? I mean, you could do both. You could do both. Yeah. But if you're not dealing with these things, it's okay. I guess you can think of it as like degrees are more friendly when working with these concepts. The radians are more friendly when working with these concepts. It doesn't mean you don't do it, though. It's kind of the experience that you'll have. Okay, so let's focus on the radians now. Radians can be defined in different ways, okay? But if you end up having like to take physics and stuff, it's used a lot for something called arc length. Okay, so I'm gonna go off of that a little bit more. Okay, so let's define a radian. So consider a circle. Oh, sorry. Consider rotating the radius of a circle by an angle theta to make an arc with length S. And so what do I mean by that? You have this circle, you have your radius. We're gonna have the radius have length R, and then you rotate the radius.
So that's what we thought.
Right here. then you rotate the radius by that angle theta. This. And then you consider the arc that you made right here. That has length S. Okay, this section of a circle is called an arc. Okay? So we define the radian measure theta to be the ratio of that arc length over the length of its radius. Yeah. There's a little ant that walks from here, this point, to this point. What's the ratio of it walking depending on the radius of the circle? Yeah. I can have a bigger circle with that same, with a smaller arc that has the same arc length as this one. So there, you have to take into account the size of the circle, which is the radius. Okay? So I want you guys to notice that this is just going to be a number. Okay? It's going to be a number. Well, let's see. Let's look at some examples so you guys can play with it. And then you can see how this works. So let's say we're asked to find the radian measure of theta. Let's do 3 different circles. Let's do one here. Let's do one here and one here. Let's say, oh man, my circles are crap. So let's say this circle has a radius of 2 centimeters. And then I rotate it up to here by an angle theta. And then you're told, you know that the arc length here is going to be 3 centimeters. We want to figure out how many radians that is. How much of that rotation happened relative to the length of this arc and how big the circle is given by its radius. Yeah.
How is that not the area of what's moving?
Because the area, if I found the area, that's called the area of the sector of a circle. Let me give you an analogy. Let's say you're making a fence, right? You're going to make a fence, a circular fence. The arc length is how much fencing do I need to make my fence from here to here, versus the area is how much, I don't know, how much lawn or grass I need to fill that whole sector. So they're they're measuring 2 different things.
So S is the radian?
No, S is the distance from here to here. The radian is going to be the ratio of that arc length over the radius.
I'm so good. I don't understand the difference between S and the radian. Like I see the math, but I'm not sure. It's not understanding what the difference is. Like,
No, that's good. That's good because that's what a lot of people think is that the arc length is a radian, and that's not necessarily true. It's the radian if R equals 1, because then S equals theta, and that's where the concept of the unit circle doesn't let you see that, because in the unit circle the radius is always 1, but the definition of a radian is for any circle. And so you have to take into account how big the circle is. How do you measure how big a circle is? Well, you use its radius to tell you how big a circle is. Okay? And so if the radius of this circle was to be 1, then it turns out that the radian is numerically equal to the arc length in this case. But the radian is not arc length. They're different things. The radian is more of a ratio between the length of the arc and its corresponding radius.
yeah, like it's that ratio, but what is it?
it's telling you how much, it's a ratio telling you how much rotation happened for this particular circle.
And
Yeah,
the rotation depends on the size.
and the rotation depends on the size, correct. So in this case, if I write this in decimal, what's that in decimal? 1.5, I would say radians. And we write that. So this angle relative to the size of this circle and this arc length did a rotation of 1.5 radians. Okay. How much arc length should I have to get 1 radian? It would have to be 2, right? So in this case, 1 radian is the rotation so that your arc length is the same amount of units as your radius. Okay, that's what 1 radian will represent. Maybe let's write that here. So notice 1 radian rotation happens when the arc length equals the radius, equals the radius. No matter how big the circle is. If the circle's humongous, then when your arc length reaches that length of your radius, that angle of rotation is 1 radian. Okay? Okay, let's do this one here. So we have 1.2 inches. And let's say I rotate it down to here. And now this whole arc length from here to here, this whole arc right there, that is 4 inches. So how much rotation happened between this circle and the size of its radius? So I would do the arc length, its radius size. Does that divide evenly? Let's see, what did I get? Yeah, it's about 3.3. About 3.3 radians. Okay. What is that? What's happening? What the hell does that mean? Okay. 1 radian is when you've rotated so that your arc length is equal to your radius, right? So if my radian is 3.3, that means I've rotated about 3 times as the distance of my radius. So I've traveled my radius a little more than 3 times distance. So 1 radian, 2 radians, 3, or about 3 radians. Okay, so when you guys see radians, it's telling you relative to the radius, how many times did you travel the distance of its radius? Okay. All right, let's do another one. Then I'm gonna have you guys try some. Okay, let's say it's 2 centimeters. And let's say you're up to here, but now you rotate it in this direction. And this is your theta now. And you're told that because you rotated clockwise from here.
So where the rotation is 0 goes,
Say it again.
where the arrow rotation is where the 0 goes.
Like where this, yeah. So right now this is the initial side, and this, but the arrow shows you that this is a terminal side.
Okay, but for like those 2 right there, the reason why it's not the inside is because it should be inside it.
What do you guys mean by inside it?
I think like the 0, like the angle.
Oh, the theta?
I don't think it matters.
Yeah, the theta is just saying, it's just the symbol to represent that angle of rotation.
Okay.
Yeah, it's kind of like if I told you this is 2 centimeters, I can write it up here or I can write it here.
Oh.
Yeah,
okay, I
Yeah,
see.
it's just like where it's labeled. Mhm.
So do radians get negative when it goes in the backwards direction?
Right, yeah, so now we're rotating clockwise, so we're gonna have to have a negative angle. Okay, so if this arc length is 9.6 centimeters, it's gonna be your job to understand that you're rotating clockwise. So I'm gonna have to have a negative angle. So I need to put the negative there. Okay? What's my arc length?
9.6.
Over 2, which I believe, oh yeah, it's nice. It divides nicely into 4.8 radians. Okay? But it's negative. So this means that if your initial site's here, you rotated clockwise almost 5 times the distance of its radius. Okay? All right, I'm gonna have you guys try some. Okay? So here, I'm gonna give you 2 circles. Say, let's have them start right here. Okay, this one will be 5 centimeters. And it'll rotate right there. And this is about 7.85 centimeters, the arc length there. And they're rotated this way. And then this guy will be here. And it rotates this direction. The radius is 2 inches. And the arc length from here to here is about 6.28 inches. Find the radians. Mhm.
Trig definitions of radians. Trig definitions within radians are on the
We rely on the unit circle, which is what we're going to start today. But then when we come back, we're going to use more of the line stuff.
Yeah.
So then help us find it for bigger circle with a bigger.
What do you want for sig figs? If you want to use it 10th place?
Let's do 2 decimal places. Yeah, 2 decimal places.
Does the unit like inches or centimeters, does that reflect the radians?
Oh, question about the units. So like this is centimeters here, and this is centimeters. So they kind of like cancel out.
Oh, okay.
Yeah, and so the result though is rotation, so we label it as radians.
So does that mean if it was, if there were 2 that were from like different units, but they had like the same number, would they be equal number of radians?
You'd have to do unit conversion.
You would have to convert them to the same units. You would have to convert them.
So basically just 2 measurements packaged into one name.
Yeah, yeah. So this is kind of saying you rotated so that your arc length, I guess, you rotated an arc length of 3 centimeters per 2 centimeters of radius. Like that. That's kind of what the radius is saying. But then that's true for every other unit. Yeah. All right. Let's see here. So here, what did you guys get?
1.57.
1.57. Okay, so that's a round though, right?
It would be 1.5.
Was it exact? Oh, sick. Okay. 1 point, let's see, 7.85 divided by 5, 1.57, you said? Positive or negative? Units? Rad. Radian, okay? Here, what'd you guys get?
Negative
Negative
3.14.
3.14.
Rounding or exact?
Exactly.
Exact, okay, negative 3.14 rad.
Was that intentional?
That was definitely intentional. Okay. From what you guys were telling me about your warm-up, this is 180 degrees turn, right? A negative 180 degree turn. What was the association you guys learned with pi stuff?
5.8.
180 was
Pi.
pi radians. So the question is why? Okay, why was it pi? Well, I round, if a circle is a radius 2, I guess let's do a little side work here. If a circle is a radius 2, there's another thing that you learn in geometry, circumference, which is the total perimeter of the circle. There's a formula that you guys learn for circumference. Has to do with area.
Yeah.
2 pi r. That's a formula you guys learned in geometry. Okay, we're going to use it several times today. So here, what's the radius? It's 2. So it's 2 pi times 2, which is 4 pi. So the whole circumference here is 4 pi. So what's half of the circumference? It's 2 pi, right? What's 2 times pi in decimals? 6.28. Okay. So if the radius is 2, this distance here is really just 2 pi inches, which in decimal is about 6.28 inches. So therefore, this rotation is negative pi radians. Okay, and pi, it's just that pi it shows up in this case when you're having, I guess, more like nice types of rotations. Quarter rotation, half rotation, 3/4, pi shows up. It shows up in there. Okay. Here, this is actually 90 degrees. It's a right angle. What were we labeling a right angle in radians using pi? So 90 degrees, you guys wrote on the warm-up was pi over 2. What's pi divided by 2 on the calculator? 1.57. About 1.57, right? So the thing is that instead of writing these radians as decimals, we write them in a more exact form with pi. And so that's what you've been doing. But in reality, it's still a decimal amount of radians, right? And this means that if the radius is 5 centimeters, when I rotate 90 degrees, I'm rotating about 1.5 number of units according to the radius. That's kind of in decimal form. That's what it's telling you. Okay, yeah.
Wasn't the first one kind of like the easiest one to demonstrate that?
Oh, yeah, exactly. Yeah, notice that the radius is 2 centimeters. 1.5 is 2 plus 1 rotation corresponds to an arc length of 2 plus 1, which is 3 centimeters. Okay. So radians is just telling you the type of rotation relative to the arc length and the radius. That's kind of the big picture. But you've learned that with these special angles, you can express these rotations using pi expressions to give you an exact radian. Okay. Okay. All right, so let's see. So so from all this stuff here, so notice that oh no, sorry. I skipped my notes here.
You shouldn't be noticing things.
I know. Not yet. I have to draw the picture first. So recall that what I just wrote earlier, but let's write it again. That the circumference of a circle with radius r is given by the formula we just wrote right now. C equals 2 pi r 2 pi r. So let's consider the following. So let's draw a little circle in your notes. What's the length of the radius here?
No.
We don't know it, we're calling it
Or
R. Okay? And so if I do one full rotation here, I do one full rotation, 360 degrees of rotation. And I asked you, and we use this relationship here. Okay? I wanted to find this angle here. Using the definition, that's the arc length divided by the length of its radius. Okay? But if you do one full rotation, the arc length is really the what? It's really the circumference. If I do one full rotation, right? So if you do one full rotation, the arc length is really just the circumference. So then what happens from here? The r's cancel. But remember that when I divide the arc length by the radius, the units is radians. Okay, so what we end up with is 2 pi radians. And this is kind of big because it's saying that it doesn't matter the size of the radius of the circle. One full rotation is always going to be how many radians? 2 pi, regardless of the size of the radius. Okay, yeah.
So radians is kind of how we interpret like the like a unit value for circumference. Like not like in portions.
What's 2 pi in decimal form?
6.28.
This is about 6.28. If I round it, let's say it's 6.3-ish, right? So this is telling you that to do one full rotation, no matter the size of your radius, when you do one full rotation, you've walked about 6 times the length of the radius. That's really what the radians is telling you. No matter how big the circle is. When I walk around it, I've walked about 6 times the length of my radius. Okay. And if I walk half of it, I've walked about 3 times, which is why it's pi. It's approximately 3.14, about 3.
So you're using your radius as like a form of measurement kind of?
Here we do. Here it matters. But what this is showing you is that the radius will always end up canceling. So it actually doesn't matter the size of the radius. One full rotation will always be 2 pi radians. Always. Always.
Is it possible for the number to be different? Like, is it always 2 pi or is it just?
The fact that this r is unknown and the algebra here cancels r says that no, you can't have a different result. It should always be 2 pi radians, regardless of r.
So that whole thing is basically saying almost 6 times around the radius.
You've traveled about 6 times the length of the radius. About 6 times the length of the radius. So yeah, let's write that down. So
Over 6.
one full, yeah, a little bit over 6. One full rotation on any circle. What this is telling you is that one full rotation on any circle makes you travel a little over 6 times the length of its radius. Which is really more precisely 2 pi times the length of its radius. And so from knowing this, right, how many degrees is one full rotation? So then we bring it back to degrees now. So therefore, we have the following result. That 2 pi radians of rotation is equivalent to 360 degrees of rotation. Kind of the way 1 foot of length is equivalent to 12 inches of length. Okay. Divide both sides by 2. And then we get that pi radians is equivalent to 180 degrees of rotation. Pi is about 3.14. So it's about 3. If I look at it just as a decimal, if I round to the nearest whole number, it's about 3. That means that whatever the size of the circle is, when you do 180-degree rotation, the arc length that you covered is about 3 times the length of the radius. No matter the size of the circle. Okay? Questions? Okay. I'm going hella deep on radians, okay? Because it's something that you just kind of forget what it really is doing. All right, so now we have these equivalences that you're going to use to convert from one to another. I did hear some of you guys, I did see some of you guys put that on your note card. And so we're going to use these here. So conversions. So to go from degrees to radians, we're going to end up multiplying. Yeah, so here, let's do a little example so you can see where this is going. So let's say I want to convert 45 degrees. I want to see how many radians that is, right? So I'm going to multiply it by something. But I want to cancel the degrees. So the degrees will need to be on the bottom. So that they cancel, and I'll need the radian up here. But how many radians is the same as degrees? 5. So we're going to multiply by pi radians over 180. So to convert from degrees to radians, you multiply by pi over 180 radians per degree. Because in an angle measurement, this is 1. This ratio here is really a 1, which is why you're allowed to multiply this number by the number 1. Okay, but it's just this whole conversion thing that's happening. So what happens to the units of degrees? They cancel. So just with the numbers, I end up with 45 times pi. And then think of this fraction as over 1. So then 1 times 180. But now the degree units canceled, so I end up with radians. All right. That reduces. I think 180 goes, 45 goes into 180 4 times. So 45 goes into 45 once. It goes into 180 4 times. So we end up with the famous pi over 4 radians. Okay. What is that in decimal? Someone help me out with the calculator.
Is it 25? No, pi.
That's 1/4.
Okay.
Pi over 4.
Since I was wondering, like if you were doing it as conversion, like in something, you would divide that 45 by 180.
That's what ends up happening when you write it as a fraction.
Okay.
Yeah.
Because that does give you 0.25.
But you would get 0.25 times pi. Okay. Still times pi. Someone help me out here. What's that in decimals? 0.7. point what?
7,
0.78. So that means that when you rotate 45 degrees, the amount of arc length you traveled is about 0.78 times the radius. Okay, times the radius. Right? See, I don't want to squish this one down here, so let's. This. All right, and then if I want to go from radians to degrees. For example, I want to convert pi over 6 radians. And so I gotta multiply it by, I want radians on the bottom and I want degrees on the top. So it'd be 180 over pi. So you're gonna have to multiply by 180 over pi degrees per radians. And so here, the radians cancel. So I multiply just the number pi with 180. And then I multiply the 6 with the pi. My units has to be radians now. And so then I do a whole bunch of cancellation with the actual numerical values. So yes, 6 goes into 180 30 times. So that's going to be, oh shit, sorry. The radians cancel. They should be degrees. My bad. So that should be 30 degrees, or you can just write the little degree symbol.
Doesn't pi radian itself cancel out? Can you just cancel it right there?
You could cancel it right here. Correct. Correct. Again, someone help me. What's pi over 6 as a decimal? 0.52. So this is about 0.52 radians. So it's about half, right? About half radians. So if I'm on a circle and my arc length is about half the length of my radius, I know I've rotated about 30 degrees. That's what that's saying from one to the other.
So the ratio still makes. I was thinking of like your sine.
Sine.
One of the two. Like if you look at like a sine.
Oh, I get you. Yeah. You're thinking the 60, 30, 90 kind of.
So it's a way of measuring not parts of the circumference, but like how much you've gone around it.
Correct. Yeah, with the taking into account the length of its radius. Yeah. Almost done it, then we'll go on a break, okay?
What did you know with after the break, will we go right on the 7.2?
Yeah. All right, so let's see. So we use this here to give us these conversions. I'm splitting up my board here into a little puzzle. Sorry. All right, here's my last remark. So in a circle of radius r, the length s of an arc. Wait, I've been putting ARK, huh?
Yeah.
It's ARC.
You put ARC.
Oh.
Yes.
Arc is like fucking arc, like the water.
Or a boat.
Or a boat, yeah. Arc, RAC. Oh crap. Sorry about that, guys.
No, I have art.
You wrote art on one.
I probably switched them back and forth. Yeah, okay. I wrote these notes when I was up in the plane, so I was like. Okay, so in a circle, of radius r, the length s of an arc corresponding to, and I'll show you guys this with a visual, to the central angle whatever that means, I'm supposed to talk about that, means of radian measure, also important. Theta is given by, and then, I want to see if we can discuss it real quick. Yeah,
Isn't arc also numbers?
that's when we're talking about them as functions. Once we get there, not there. Okay, so what's the formula that we use for radians? S over R. So if we know the arc length and we know the radius length, we can find the radians, right? What this is saying is instead, you don't know the arc length, you do know the radius, and you know the radian measure of theta.
So would you use those six to try to find the part?
Exactly. So if I'm trying to find this, how algebraically, what can I do to this equation to get R by S by itself? Yeah, just multiply both sides by R, and so then my arc length S will just be the radius times theta. The radius times theta. But it's very important, guys, that your theta is not in degrees. It's in radians, because that's how this was defined.
So would that be the conversions?
That's where you do the conversion stuff. Yeah, like if I'm told of a problem in degrees, how do I figure out the arc length? Okay? And so that's exactly what we're gonna do right now. Take a look. I'll have you guys try this out. Actually, let me do practice because I want you guys to do it. Practice. Find the arc length.
It's where Noah's arc factors in.
Yeah. So let's say that this circle is the radius is 2 inches. And you know that you've rotated 60 degrees. What's the length of that arc? So maybe try to figure that out. Maybe in your notes put that this is called arc length. Guess you need to reference it. Dutch Brothers. The 60 would be, it's in degrees. So it's like this one was in degrees. So somehow you want to use this and what we just discussed here. Okay?
I'm trying to figure out which number would be the circle. What's that called?
Are you talking about this?
Data, yeah.
Well, that's what you're looking for, but you're only looking for this part, not the whole circle. The whole circle, we know for sure will always have to be that.
Okay.
Yeah. We'll see.
Right?
Say it again?
This circle is 4.5. It's 2 inches.
It's 2 inches and you rotated 60 degrees. What you're trying to find is this arc.
Yeah,
Yeah. Confirm it.
I think we'd be in the same.
Okay. You seem like that's sense.
Oh, the circle is 4.5.
And I remember you put that on the block, so that would be so. Oh, okay.
Oh.
Right. That's what it is. Right. Correct. Yeah, and it's just coming over
Well, I don't want my next. And then you're fine.
What did you? Let me see. I didn't. It would be. So. Yeah, that's radius. Our point equals radius.
Oh, yes. So there's the, see how we did so there? So,
Like it's very. So you put.
Yes. Okay.
That's what was missing. I didn't see. Yeah, so you're gonna. I don't know how it's sounds.
My dad was trying again. I just said that pi over 3 is close to 1. Wait, I'm not sure about that. Actually,
Never mind.
it shouldn't be.
All right, guys. So if I try to use this formula here to find my S, would it be, what's my radius here? 2. Would this be okay to do like that?
No,
Why is that not okay?
because you have to convert it to radians.
Because you need to make sure that angle is in radians before you do that multiplication. So you don't want to do this yet. What you need to do first is convert 60 degrees to radians.
60 degrees and convert it afterwards.
You can, yes, you can. Okay, so let's see. So we're gonna is it this one or this one? It's multiplied by,
Yeah, that one.
okay, so we need 60 degrees times for 180. Oops, sorry, degrees, radians. These suckers cancel. 60 goes into 60 once and into 180 3 times radians. So that's the angle you're going to want to use in radians. So it would actually be 2 times pi over 3 radians, which is going to be 2 pi over 3, but it's arc length. So if I convert this to decimal, did anybody?
2.09.
2.09, what are my units? Am I talking about angle as my answer, or am I talking about distance traveled? Distance, inches. It'd be inches. Okay. Yeah, question.
Oh, I ended up with 2.1 because I think I rounded at a different time.
Oh, 2.1 would be, it depends. What website will tell you or not say it faster. Yeah, question.
So wouldn't be 2.09 times the radius?
This guy? I guess how, if you, to get this number, you already multiplied by 2,
So
which is the
pi over
radius.
3 is what you're doing times the radius to get it.
Correct. This is the R
Mhm,
and this is the theta in radians.
For sure.
So would it be also fine if like someone did like you pi over 3 and just be more exact?
Correct. Yeah, that's why I circled both of them.
Okay.
Yeah, you can also just, WebAssign will probably want you to do it like that, and unless it says, please round to the first decimal place or second or something. It's just, I want you right now to practice putting it into the decimal, because I think it's helping you see what it's really doing. Because when things are in pi, immediately people think radians. Okay, but right now this question is about arc length. So it's actually not radians, it's inches. Okay, guys, let's take a break. Good job. Come back at 2:17. 2:17, and then we're gonna start Trig. Introducing Trig here.
Wait, that wasn't Trig.
That was angles. That was angles. All right, bring it back. We're almost done. Last half of class. And then last text, please. Gotta move on, gotta move on. I'm recording, right? Okay. All right, guys, so we had some practice with radian angles. Okay. Now we're gonna use this concept with the unit circle that will then help us define the trig functions that you guys learned back then. So this is gonna be from section 7.2 to 7.3. So unit circle, or uses unit circle and talk about trig functions. Do this here, then you guys are done with math for the week or lesson wise, okay? Okay, so to kind of motivate what's gonna happen, little bit of history, okay? So many years ago, people wanted to study the stars, astronomy, and to help them with that, angles were involved. But to help with angles and distance of things, the creation of trig functions came about. Okay. Since that has to do with circular shapes and angles, the history as I read it and understand it is there's a relationship to back then in India, folks were using bow and arrows. Okay. And given the arc of their bow, so this is the bow here. Okay. It goes a little more in front. They wanted to know, okay, if my bow is like shaped this way, with this certain arc, how long is the length of the cord that I need? Okay. And so to help with that, they use circles to pretend to be that arc. Okay, let's say this arc is over here, this arc right here. They put it on the XY plane, and then they wanted to study, well, I want to figure out the length of that cord similar to the one this one is right here. And so to help with that, they said, well, we can find length of half the cord, then we just double it, and then that'll give me the length of the cord. Okay. And so from what I was reading, there was a lot of mistranslation. Okay. We're going to start with the sine function. The sine function roots from the Latin word sinus. And from what I read, there's a whole bunch of mistranslation between the Arabic language and the Hindi language, where the original concept was half chord. Okay. So originally they were using a word to represent half chord. I think it was in the Hindi language. Then they translated to Arabic and there was some mistranslation. And then from there, they translated to Latin. From that mistranslation to the word, to the Latin word, so it went from Hindi to Arabic. And then to Latin. To use the word sinus. Which, from what I read, has nothing to do with half a chord. Okay. But that's kind of where the origin of this word sine is gonna come from.
Isn't it the part of the Y axis though? Like half a chord, like half of the
Yeah.
Y.
Exactly, yeah, yeah, and so that's exactly why Y has that relationship with. Sorry, why sine has that relationship with the Y chord, that's where we're going. Yeah, so that's kind of where this is stemming from, okay, is that there was this problem of finding the length of this chord. They modeled it using a circle on the XY plane, so to find this point here, to find that length here, if I have the coordinates of this point, as Alexa was saying, that length here is the value of the Y chord. Okay? And but that length that they were looking for is what they were calling the half chord or sinus or sine. Okay? And so we're gonna model. Okay?
Yeah.
We're gonna model this
Are
with
you
the,
about to talk about sine and cosine and tan?
you know it, yep. And so, to start here, they used the most basic circle, which is the circle radius 1, and then they plotted it on the XY plane. Okay, so we're gonna start with that. We're gonna consider the unit circle given by x squared plus, anybody remember the equation? Y squared equals a radius squared, which in this case is 1 squared, which in this case is 1. Good. So we have our unit circle here on the XY plane. We put that circle here of radius 1. Let that come out. It's still 1. Okay. Our angles here, your textbook is going to call an angle in standard position. And what that means is that when you place the circle on the XY plane where the center of the circle is on the origin, your initial side will always be on the positive x-axis. You're always going to start from there with your initial side. And then you rotate from there. That's what the textbook is going to call standard in standard position. So let's say you rotate it right here, or actually, let me go off of this here. Let's say you wanted to figure out color. You wanted to figure out the length of this chord from here to here. Okay. When you have a random line segment crossing a circle, that's called a chord. Okay. So if you wanted to find this length here, well, this is a point that has an XY coordinate, and I can think of rotating my radius, radius 1, rotating it so that the terminal side coincides with that point. Okay, you rotate it by your angle theta. And then as Alexa pointed out, well, if I want to figure out how long half of the chord is, that is going to coincide with the distance of the y with a y coordinate, right? That's going to coincide with what value that y coordinate is. And it's going to coincide, this length here will coincide with the x coordinate, right? If I told you to plot this x coordinate, this point here, you would go x units this way, y units up. It's kind of like rise over run, and actually I'm going to show you how that's related. Yeah.
So does that mean the terminal line is the x, like that little, the half of the x? When you before you rotate it.
So ask your question again.
You said you moved the terminal line?
When you draw your angle, your initial side starts on the positive x-axis, and then you rotate so that the terminal side coincides with that point.
So that's now your terminal side.
This is now your terminal side right there.
Where was the first terminal side?
The terminal side is where you end up after the rotation.
Oh, okay.
Yeah.
So there's not a first terminal side?
I guess the first terminal side is the initial side.
The initial one in this case is so.
It's this bad boy right there, and that's always gonna start there. Yeah. And so let me just kind of throw that out here.
So terminal
So-
and behavior or whatever, endpoint.
Yeah, and I don't want you to get confused on the homework, so let me just do a little note here. We're gonna say an angle is in standard position when the initial side is on the positive x-axis. Like the positive side of the x-axis. So for example, don't write this part. If I do this here and I consider this angle, if I consider this angle right here, that is not in standard position if I rotate it like that, because the initial side is not on the positive x-axis. That's what that means. So we're not going to consider that. We're going to consider angles that are in standard position.
Positive as the right side.
Positive is the right side of the x-axis, correct? Okay. So here's the plan, okay? We're gonna define these trig functions off of this unit circle definition. Triangles are obviously gonna be involved. But when you come back, we're gonna kind of redefine them again through the triangle version definition with SOHCAHTOA and all that stuff, okay? But right now, we're gonna focus on the unit circle part, connection. Both are used a lot in calculus. So I want to spend time kind of on both of those. Okay. So we're going to use this shape to define our trigonometric functions on angles. You guys are dropping things. You want to get it? Okay. You guys are nervous on the trip. You're like, okay, so the first one is sine. And again, using this relationship, sine is helping us find this distance right here, according to the angle of rotation. So that's why we're going to define sine to be the value of that y value at that point. Okay, this is the unit circle definition of it. So I'm going to define, bro. Oh, I thought someone else. That's okay. Don't get too nervous, guys. Sorry. Okay, so I'm going to define. Actually, let's just remove the f of that. So we're going to say sine of an angle. This angle right here, in this particular picture, is going to be defined to be this value y, because it'll correspond to the length of half that chord. Okay. And so notice that in this case, it's just the y coordinate on the unit circle. And it's important because we're going to use the unit circle to define this. Cosine, written as cos of the angle, is going to correspond not to this length here, but to this length, according to that point. So that's going to be defined to be the x coordinate on that unit circle. The x coordinate on the unit circle. Then comes our famous tangent. Written as tan of theta. Which, and there's different ways to approach it here, but the textbook is going to start by saying it's the ratio of y over x. Okay, what's the ratio of this x coordinate over this y coordinate over this x coordinate? But as Alexa, you were mentioning, y is defined to be sine, and x is defined to be the cosine. So yes, it's also sine theta over cosine theta. But there's actually a relationship that tangent has with this shape as well, that most students don't see or probably didn't fully grasp. Okay. I start with my radius here and I rotate it theta angle, right? Theta radians or whatever unit we're using. And the point it corresponds to is this point. From here to here, if I drew a line crossing the radius, what's the slope of that radius? What's the rise? Y units over x units. So that's the interpretation that you can use to help you with this, is that the tangent of this turns out to be the slope of the radius rotated by theta. Okay?
Is there a situation where it wouldn't be theta?
Well, theta is that angle of rotation.
Well, like with the sine, cosine, and tangent, it's like sine theta. Is there any situation where it would be sine something else?
Theta is just a variable to represent an angle. It's just to represent an angle. I can, yeah, sometimes it'll be like sine of x, or it'll be the sine of a, sine of w. It's a variable to represent the angle. Okay. All right, and then to each of these three functions, you have what's called the reciprocal trig functions, not the inverse. That's it. We're going to do that later on. The reciprocal trig function. Okay. And so you remember what's the reciprocal of sine? Not cosine. Cosecant. Cosecant. And so that we write as CSC of theta, which we're going to define to be the reciprocal. So 1 over sine of theta. But since sine of theta is going to be that y value on the unit circle, cosecant theta is 1 over y, or the reciprocal of that y value.
What is it?
Say it again.
What is cosecant?
It's the reciprocal of whatever this y value is.
So it's the reciprocal of sine.
So it's a reciprocal of sine.
Why isn't it something that says like in sine or something that says like not sine? Why is it cosecant?
So there's going to be a difference between the inverse of sine and the reciprocal of sine. Those are going to be two different functions. Yeah, so that's why we can't use like inverse notation. All right, reciprocal of cosine, secant, which is just going to be the reciprocal of the x coordinate, but we're going to write it like that. Secant theta is a reciprocal of cosine, so 1 over cosine. But cosine is defined to be that x coordinate, so it's 1 over that x coordinate. And then the reciprocal of tangent is going to be cotangent, written as cot, C-O-T theta, which is going to be defined to be the reciprocal of tangent, so 1 over tangent. But tangent is defined to be y over x, right? So let me do a little algebra down here. 1 over y over x,
One time it's X over Y.
which is really 1 times the reciprocal of this, x over y. So the reciprocal of tangent is just the reciprocal of y over x. So it's x over y. Sorry, guys, all those definitions got a lot of right. Apologize. Yeah, question.
Why did they make it so that the one that has cos in front of it isn't the one for cosine?
I agree. Yeah, it makes you think that co is like the opposite or
I
something.
remember because it's opposite, I say, like, whenever I think of the word sine, I think of cosine, and CSC with like cosine, so you remember it's.
Well, does it have to do with the graphs more than a thing for these two?
It is gonna have to do with the graphs of it, yeah, but correct. I see what you mean though. Yes,
It seems misleading.
it does seem misleading, yes. Because this one doesn't, right? This one looks friendly.
Yeah.
Okay, let's get a quick feel. Just kind of play around with it on Desmos. Let's see. Let me share my screen. All right, let's go right here. Okay, so look, I have a circle here. So right now, let's say I was trying to draw a radius. I couldn't do it in a minute. But pretend you have a radius going from here to here, okay? And so I've rotated the radius up to here. So whatever that angle is, let me put it somewhere here. Let's say I have it right here. And I have the radius connecting from here to here. There's an angle of rotation that happened with, right? What's cosine of that angle? What is it? If I rotate my radius like this, coincides with that point, and I've rotated by that angle. I don't know the angle, but I know from this definition, what's cosine of that angle? The x-coordinate, 0.89. What's sine of that angle? 0.456. That's what these definitions are saying, okay? Versus if I rotate it, let me see, let me get rid of, let me do this, give me a second. There it is. Let's say I rotate it like this instead. Like that. Okay. Now I've rotated by a bigger angle like this. I don't know the angle, but what's cosine of that angle? 0.44, and sine of that angle? 0.89. I'm on the unit circle, right? What's going to be the biggest value for cosine? What's the biggest thing cosine can be, no matter where I rotate? Why is it 1? Because that's the biggest x-coordinate that you can have on a unit circle. What about sine? 1, because that's the biggest y-coordinate I can have on the unit circle. What's the smallest cosine can be? I guess smallest is a bad word. What's the most negative it can be? -1, because on the unit circle, that's the most negative x value that you can have.
It's confusing. I'm about to say it would say smallest, and I would take a moment to realize it meant negative.
Yeah. So cosine is the x-coordinate. So the biggest it goes is 1, and then it shrinks, the x-coordinate shrinks, then it goes down to -1. And then if I keep rotating, what happens to the x-coordinate? It gets bigger again, and then it goes back to 1. And it just keeps repeating over and over and over. The x-coordinate goes from 1 to -1, 1 to -1. We'll explore more of that later. Okay? If I have an angle of rotation right here, and I took tangent, is the value of tangent going to be positive or negative?
They're both positive.
With two answers to it. One, y over x. And in this case, it's a positive y over a positive x, it's a positive. But if I think of it as slope, is it, if I'm walking from left to right, positive slope. Okay, what happens to the tangent as I rotate it closer and closer to 90 degrees? The slope gets bigger until I get to 90 degrees. And then what's the slope of a vertical line? It's going to be undefined. But also it's undefined because I'm doing y over x. I'm doing 1 divided by 0, which is undefined. So you see kind of like different points of views, okay? What happens if I rotate 180 degrees and I end up over here? What's the slope of my radius? 0, because it's just a horizontal line, but also 0 divided by -1 is 0. Okay? All right. All right, now let's play with it now.
The cosecant and the secant do this looks like something on the graph, like, or do we, like, is it implied with the map?
It's going to be kind of more of just a reciprocal of those coordinates. Later on, we'll look at the graphs on the, yeah. And then they're used for like trig identities and all that stuff. All right, guys, let's play a little bit. This is what your homework, the last part of your homework will look like. All right, so we're going to, still sharing my screen here. Okay, so let's evaluate all 6 trig functions for the angle theta corresponding to point P with x coordinate x equals 2/5. And in this case, the problem comes with a little picture. Here's your unit circle. But you're told that P is located right here. And the angle of rotation is like this. This is your theta. And all you know is that this point P has an x coordinate of 2/5. That's all we know. Right? And we don't know the actual angle. We just know that it rotates so that happens. All right, so all we know, P has coordinates, x being positive 2/5, but we don't know the y coordinate. Okay. What can we answer from those 6 trig functions? The only things that use x coordinates are this one, or the things that only use x coordinates are this one and this one, right? Everything else we do need to know the y value. So maybe before we do that, let's find that y value, okay? So here's where the triangle shapes start to come in. You guys remember that chord that we were drawing? All right, so I'm gonna draw half the chord so that it goes towards the x-axis. And because it's going straight down, I have a right angle right there. And so from what we discussed earlier, we know that x coordinate is this length. But we don't know the y length. This is too small, so let's zoom out. Make it bigger. Okay. Let's see what, this is where you're gonna need to kind of like put things together, okay? Do you know how long this side is here? What's this called for a triangle? Hypotenuse. Which it is the radius in this case, that's fair, yeah. So the hypotenuse is the length of the radius, which is what? It's on the unit circle, so the radius is 1. No, the radius is 1. Okay?
Does this look like A to A, root, A, root 3?
Later on that will come up. Yeah. Okay, what else do we know about this triangle? This short side is this short side, right? How long is that? That is the length of the x coordinate. So we know that this is 2 bits. And this length is supposed to correspond to the y coordinate, which we don't know. That's the one we don't know. Okay? So then you're going to bring in your knowledge of triangles and use that famous theorem. Start with the P. You're going to use the Pythagorean theorem to help you find the y. Okay? And then you bring in the Pythagorean theorem. Pythagorean theorem, but also this point lies on the unit circle, right? What's the equation of the unit circle? It was x squared, y squared is equal to 1. And notice that this equation is going to tell you the same thing that you have here. Okay? We just said that x, that length is 2/5 squared. That's this squared, plus the length of y, which we don't know, equals a hypotenuse squared, which is again also 1. Okay? The Pythagorean theorem, but also the equation of unit circle. They both kind of, in this case, coincide, telling you the same thing. So then you're gonna have to solve for y. See, 2/5 squared is gonna give you 5. Then we subtract both sides by 4/25. Then you get y squared equals 1 minus 4/25. We gotta subtract fractions, so I'm gonna convert the 1 into
21/25.
convert it into 25/25. So this is just 25/25, so I have common denominator. So then I get 21/25. Get y by itself by square rooting. What do you have to do when you square root?
Plus or minus.
Plus or minus. What's the square root of 21? Is that a perfect square?
No.
No. Is 25 a perfect square? Square root of 25 is 5. Then you have to realize where the point lies on the quadrant.
Like.
Will this y coordinate be positive or negative? Negative. Because it's under the x-axis. So then you're gonna use y is negative root 21/5. You can see about that? Okay.
Can you simplify it?
21, does that factor into any perfect squares? I don't think so, so then we would be.
So you wouldn't want to just do it in a calculator and put in this one?
No, leave it like that, leave it like that. So now you found the y coordinate. It's negative root 21/5. So now we will, as long as I have these two, I can figure out everything else from here. Okay? So sine of my angle is going to be the x coordinate of that point, which is 2/5. cosine of that angle is gonna be, oh shit, I fucked up. Thank you. What is sine gonna be? Yeah, negative square root 21/5, and cosine is the exponent. Sorry about that. All right, here, be careful with tangent, how you plug it in on Weber sign, okay? It's gonna be the y coordinate, which is negative root 21 fifths over the x coordinate. And then you're gonna have to simplify it. That's this fraction, negative 21 fifths, root 21 fifths, times the reciprocal of that, which is 5/2. So it's negative root 21/2. Just be careful. Once I know these three, these are the reciprocal functions. So you just flip, you just do the reciprocals of all these. And so we have that cosecant of theta is a reciprocal of sine, negative 5 over root 21. But then you rationalize that. Rationalizing means I don't want a fraction with the square root on the bottom. So you multiply top and bottom by that square root. Root 21 on the bottom, root 21 on the top. So you get negative over 21. Okay. And then the reciprocal of cosine is secant. Reciprocal is going to be 5/2. That one's cool. And then cotangent. The reciprocal is going to be the reciprocal of tangent. That's negative 2 over root 21. So again, we deal with that rationalizing business. So we get negative 2 root 21 over 24. Okay, I'm gonna have you guys try one, okay? Hold your books there. So notice that for this problem, we only had one coordinate, but we needed to know the other one. We would be able to solve everything.
Is the what was saying worth so many points because it's gonna ask for every like sine, cosine, like all of those.
Exactly.
Problem.
Yeah, exactly. All right, so evaluate all 6 trig functions for the let's just say for theta corresponding to a point P. I'm not going to draw a picture this time. I'm just going to say in quadrant 3 and where the y coordinate, where y will be negative 3/5. Okay. You want to draw your own picture to help you out? Highly encouraged. Let's see something real quick. The sound of pain. Try it out, try it out.
Well, it goes 1, 2, 3.
Oh.
You need help with the quadrant stuff, let me know.
Correct. Yeah, you don't know the actual angle, you just know that it's the end of somewhere there. Correct. See something. Hmm.
Remember, you're not gonna know the exact angle measurement, you just know where it'll rotate.
Oh, wait, do you want to get into this?
It doesn't matter in this case. You need to know where the rotation is at. All right, if you haven't yet, can I just have you check in real quick with your classmates? Make sure you guys are on the right track. Just do a quick little check. Little check.
Wait, why is it? I got a 4 or 5, like 4, and I got all these. Okay, I've got all the. Yeah. So 3 and 4. Could get yet or? Always reason. Yeah. I'll be up close.
So. the farmers they want to talk depends on the court. So what I'm trying to find X.
You're correct, Renee, trying to find you out of this.
So how do I know it's not just like X and there is really depend on where
They gave you the.
some. Oh, one more question. So since it's a negative, so that means it would be negative, like subtract. like,
No,
or
because
internal.
you're doing -3/5 times -3/5, so
So it's
positive.
Okay.
Wait, no, I got the same. Wait, I got positive.
I got negative because the third quadrant, you know what, the x axis was negative. That way.
Do that, just like,
Yeah, okay.
well, but when you multiply it out anyway, it'll turn it's positive. But going, but when you divide them on the tangent, that would turn it's positive.
Yeah, but the x coordinate alone. Which should be negative.
It just takes.
But if it was negative, we know that would still. Square.
But that, and that.
You might.
I was trying to build in what's on this course, and it's on the negative. I'm giving you I didn't. Right, and for a negative. Virtually.
Because we figured out. Yeah, and for the one.
Right, yeah, that makes sense.
So like, just like.
I mean, it's all the same. It's all the reason you're going to see this. It's red.
You move this.
It's negative.
I don't know, like go out and got creative location. And then I think I did the graph wrong because I looked at my numbers. Like. Across the numbers where you can see the one. Not bad. Yes. Correct. No, the next one is here, I think that's correct. We want to get rid of. Get rid of it.
I just looked at a fraction.
Divided on.
Yeah.
Multiply it by the reciprocal instead of dividing.
You want
And then you can cross out.
Your final. Final.
Well,
Yeah.
if you. We'll go to five, right? So five is. So in.
Oh,
So
sorry.
it's. You.
Yeah, you're all good. So you just did it right. You just did it. We know this.
Yeah.
But-
Oh, no.
Yeah, you're on the, you're doing everything.
So that's nine.
I have no idea what.
That's what I was expecting.
Took me a while.
You see how it was done?
So, these 60 over here.
All right, guys, let's see real fast. My recording still, yeah, okay, so. You have your circle, some people are drawing your circle, quadrant one is. Here, this is quadrant one, quadrant two, quadrant three, and then four. So our point is gonna be somewhere in this quadrant. We don't know exactly where. But we know it's on this quadrant here. And so therefore your radius rotated from the positive x-axis all the way so that it coincides with that point. So this is the angle that it rotated like that. Okay, we just don't know what it is, but we know that it's some picture like this ends up happening. And what else do we know about this point?
It's negative 3.
3/5, and we don't know
The X.
the x. Okay. So as we did with this example, if I draw half a chord so that it goes toward the x-axis, like this, I create a small right triangle right here. What is the radius on the unit circle? That's gonna have to be 1. Do we know this side or the horizontal side? The vertical ones, because that coincides with the y coordinate. So we know that this is gonna have a y coordinate of -3/5. We just don't know the x. So you can visualize it this way, or you can think of it as a point on the unit circle. So that on the unit circle, I don't know my x, but I do know that y is -3/5. You could do it in the triangular explanation with Pythagorean theorem, or on the unit circle equation. Either way, you end up with this. So in this case, I think, what is that? X squared. Is that 9/25?
Yes.
You subtract 1 by 9/25. What did you guys get when you do that? It's 25 over 25. Yeah, 16. Oh, nice. This one turned out to be nice. So you square root both sides and you get
Plus or minus
5. So now do I use the positive 4/5 or the negative? Why? You're in the third quadrant versus if you're in this
First or fourth.
fourth quadrant, y would still be negative, but x would be positive in this case. Okay, so then now we know that this is really going to be positive 4/5. So then you use, now we have enough information to help you find sine and cosine of that angle. But getting these is going to be the hard part. Okay? Question. So on the homework, be careful what quadrant you're in. Otherwise, you're going to get the whole thing, or you're going to get some of them wrong. So then sine is going to be of this angle of rotation. -3/5. So then cosecant. Sine is the y coordinate. Oh, good. -3/5. The reciprocal is cosecant. So the reciprocal is going to be -5/3. Cosine is the x coordinate on the unit circle, 4/5. JK. Thank you. So the reciprocal is cosine secant. So -5/4. And then tangent here. It's going to be, it reduces to 3/4. Yeah, so -3 the y over the x reduces to 3/4 positive, right? Does it make sense that it's positive? This is the slope of the radius is positive. And so then cotangent is just the reciprocal.
What are the reciprocals even for? Like what use do they have?
I know graphically they have a relationship to the graphs that we're going to explore later on of these. Let me think about that question. Like in terms of applications and stuff. All right, guys, you look like you're so ready to leave. Okay, it's like this one's got it back. So what I'm gonna do, and I feel like the next part is very important. We're gonna do the special angles, like all that stuff. So that's too fundamental to just cover fast. So what I'm gonna do is wait till next time we meet to cover that, which means I'm gonna remove like the last 3 homework problems. Okay? You okay with that?
Yeah.
Of course you are. Okay. All right, guys. Well, we'll stop here. Yep. Good job. Enjoy your spring break.